Welcome to chapter 15. We'll be talking about benzene and aromaticity. This is a review slide for the previous chapter. Do you see that this is a six-membered ring with a double bond? So we number those. We can work this retrosynthetically. So we put an X on the 1 and the 6 and the 4 and the 5. And you see how this is cis. So that means this has to be cis. That is the diene O file. And then the diene comes from this part here. The diene would be this five-membered ring here. And it says, what is the dienophile? So this is your dienophile, and your dienophile would be D. Like I said, we're in chapter 15. We'll be talking about benzene and aromaticity. Okay, so this is benzene. Benzene has the molecular formula of C6H6, and it took Kekulé like 40 years to figure out what the structure of benzene was. He did have the molecular formula of C6H6, but he did not know what the structure was. And this is bromine, and bromine is an orange liquid. And when you have a regular double bond, it undergoes electrophilic addition to give you the addition dibromide product. But there's no reaction when bromine is added to benzene. So this really puzzled Kekulé. And so I think he was having a dream one night, and he dreamed a snake came around and bit its own tail. And that's when he woke up and realized this was the structure of benzene. So benzene doesn't act like a double bond, but you can get substitution to happen if you use a Lewis acid. So this is a Lewis acid, and so when you have benzene and you add bromine with the Lewis acid, you can replace one of the hydrogens here with a bromine. So you can get a substitution product where one of the hydrogens get replaced with a bromine, but you have to add a Lewis acid to the bromine. So this is where we have a new functional group called aromatic. And these reactions, you're going to learn a thing called EASE, which is electrophilic aromatic substitution. So this is Kekulé's description, and you can see it's an equilibrium where, so this actually would be a resonance structure. So make that correction. Okay, so what is unique about benzene? It has a six-membered ring, and it has 3 degrees of unsaturation. It's planar, so each one of these carbons are sp2, which makes it flat. And so it's planar, everything's sp2. It is a ring, six-membered ring structure. All bonds are equal length, so even this single bond and the double bond are equal length. So this is benzene. The electrons are delocalized. Sometimes people will do this. I do not like that, because when we draw reaction mechanisms, we need to draw these electrons going from here to an electrophile. And this is less information. You don't have to know a lot about the bond length. Just know that this is planar. These are sp2 carbons. So the hydrogens and the carbons are 120 degrees from each other. And an sp2 carbon, that means you have these unhybridized p orbitals above and below the plane. And so this is where the electrons kind of overlap, almost like a ring. And so there's the electrodensity above and below the plane. So to name these, this is ethylbenzene, tert-butylbenzene, chlorobenzene. So you just kind of add the substituent and then benzene. You do need to know toluene. These are common names, and you should learn these, phenol and aniline. Now, this you also need to know when you have two substituents. So when you have a disubstituted benzene ring, then most of the time you're not going to see it 1,2-dibromo. It's just going to be O for ortho. So an ortho is a 1,2 disubstitution. This is a 1,3 disubstitution, so this is meta. And then this one is a 1,4, and it's para. And that's going to be important because we're going to talk about reactions that are ortho-para directing, meaning the substituent that you add to the ring will be either added to the ortho or para carbon, or some reactions will be meta directing, and you would add a 1,3 product. Okay, so this is, you can alphabetize them. So B comes before C, so ortho-bromo chlorobenzene. So that's applied that the 1 is for chloro and 2 is bromine. Metafluoro nitrobenzene. Para-bromo-toluene, so this is toluene. Ortho-nitrophenol. When you have more than one, then you need to put the numbers, you need to give them the lowest possible set of numbers, so that determines whether you go clockwise or counterclockwise, and you put them in alphabetical order. As you can see, C comes before E, which comes before P. When benzene is named as a substituent, you call it a phenyl group. Sometimes you'll see it abbreviated like this, like phenyl CH2Br. I would expect you to be able to draw the line structure for your reaction, because this would not be helpful. Phenyl OH is, I would expect you to be able to draw that structure, phenol. A benzyl group, I expect you to be able to draw the benzyl group out. We've talked about benzyl, and this is a phenyl group. So a benzyl group has this extra CH2 here, and a phenyl group is bonded straight to whatever the carbon rings are, carbon chain. This is showing you IR, mass spec, and NMR. You do have some slides at the end to look at those. Some review slides from Organic 1, but your IR absorptions, usually you're going to see something around 3,000. NMR is probably the most important. This is between 6 and 8 parts per million, and the benzyl is around 2. This is also a review showing you that you should get, these are chemically equivalent. You should get 3 signals. For a carbon NMR. You're only going to get 2 signals for a proton NMR. So you would get 2 signals. And here, same. Okay, so here's benzene, toluene, para-xylene. These are some of your simple compounds, aromatic compounds. You also get polycyclic aromatic hydrocarbons. Those are carcinogens. Naphthalene, that's the ingredient mothballs. So if you smelt mothballs, that's naphthalene that you're smelling. That is a simple polycyclic aromatic hydrocarbon. These are all flat and planar. They're very carcinogenic. Carcinogenic means they cause cancer, and so they intercalate the DNA, and so they cause some DNA translational issues. This is an example of a polycyclic aromatic hydrocarbon in cigarettes and the tobacco plant. Here's some more polycyclic aromatic compounds. These don't have stereocenters because they're all sp2 carbons. Remember, for a stereogenic center, you have to have a carbon bonded to 4 different groups. So you're looking at sp3 carbons. Drugs that contain a benzene ring. So you see Zoloft has 2 benzene rings. Viracept has 2. And Novocaine has 1. Okay, so benzene is aromatic, and it's very stable. Very stable. So it has very lower energy. So you look at benzene here, and if you take benzene versus the diene versus cyclohexane, and you do catalytic hydrogenation, you get the same alkane, the cycloalkane. And then you can measure the difference here. And you can see that for one bond, it's 120. For 2 bonds, it should be 240, negative 240, but it's 232 because it's conjugated. So because it's not 240 and it's 232, that's an extra 8 kilojoules of mole of energy in conserved with the conjugation. And then here, it should be 360 and it's 208. So now we're looking at a lot bigger difference than just what you see in conjugation. So it's more stable than 3 isolated double bonds. And so this is the reaction in which you go to the cyclohexane and you measure the difference in that energy, hypothetical and actual. Okay, so like I said, when you react benzene with bromine, you get no reaction. No reaction. Okay, so, but if you add a Lewis acid, iron, bromide, and bromine, then you can get EAS, which is electrophilic aromatic substitution. And what you're going to see is this generates a very strong bromine electrophile. All right, so let's name this compound. You see that this is toluene. So this is toluene. And then this would be ethyl. And then where is it relative to the substitution? So it's a 1,3, which is a meta. So meta-ethyl toluene. So B is your answer. Okay, so one thing you need to be able to do is classify compounds as either aromatic, non-aromatic, or anti-aromatic. So benzene is aromatic. This compound is not aromatic, so non-aromatic or not aromatic. So this is not aromatic. One of the reasons, and there's some criteria. Number 1 criteria to be aromatic or anti-aromatic is it needs to be cyclic. And you see, this is not cyclic, so it's not aromatic. Another 2 thing you have to have is alternating double single bonds. So that means every carbon or element needs to be sp2 conjugated. So, and it has to be planar. So number 3, you just make this 2. Number 2 is planar. You can make that 3 as planar. So usually, like if you get like 8 membered rings, this does this like tub shape. So you'd have to actually look that up to know that that's not going to be planar. So you wouldn't know. So they can, scientists can take cyclooctane, octatetra, reacted with bromine liquid, then you can get your typical electrophilic addition reaction where bromine will add. You don't have to add a Lewis acid. Number 3, your molecule must be completely conjugated. So every carbon here is an sp2 carbon. So it's alternating double single bonds. Here, these are sp3 carbons. So this is not going to be aromatic because it's not fully conjugated. So you see that this is cyclic, it's planar, and it has to be fully conjugated. This you would find that because it's sp3 is not planar and it's not fully conjugated. This one is an sp3, so it's not aromatic. So if it's not fully conjugated, then or cyclic, it's not going to be. Okay, and then the last, so if you have all three, so if you have 1, it's cyclic. Number 2, it's planar. Number 3, it's fully conjugated. Okay, so then you have to decide it's either going to be aromatic or it's going to be anti-aromatic. If it doesn't meet these 3 criteria, then it's going to be not aromatic. But when is it going to be aromatic versus anti-aromatic? And so an aromatic compound must have 4N plus 2 pi electrons. And this is just some formula. So you have to count. So here you want to count your pi electrons. So here you have 1, 2, 3, 4. This is 4 pi electrons. Now, this is just a number. N is just 0, 1, 2, 3. So you do this 4N plus 2 pi electrons. This is for aromatic. So what's the number if N is 0? So 0 times 4 is 0 plus 2, so 2. And then if N is 1, 4, 5, 6. If N is 2, 8, 9, 10. So these are the number of pi electrons. Do you see that for anti-aromatic, it's 4N. So that's 0, 4. We're just doing 2 times 4 is 8. You see if it has this number of pi electrons, it's anti. Well, 4 pi electrons. Cyclobutadiene is anti-aromatic. Anti-aromatic is less stable. So aromatic is the most stable. Then not aromatic is more stable than anti-aromatic. So this is called Hückel's rule and refers to the number of electrons. And like I just said, this is just some formula. And you put any random N means nothing. Okay, N means nothing. They're just numbers that you put in. But this means everything. This, if the number of pi electrons are any of these numbers, then that means it's aromatic, if it meets the other 3 criteria. So the ones that are anti is if it's 4N, which would be 4, 8, 12. So you need to be able to classify compounds as aromatic, anti-aromatic, or non-aromatic. So an aromatic has a cyclic, planar, completely conjugated compound with electrons. Anti-aromatic is a cyclic, planar, completely conjugated compound with electrons. So you see that these are the same. So this one, aromatic, is Hückel's, and this is anti-aromatic. So you got to count your pi electrons. And then non-aromatic would be a compound that lacks one or more of the following. So if it's not cyclic, then it's going to be not aromatic. If it's not planar, it's going to be non-aromatic. If it's not completely conjugated, it's going to be not aromatic. You don't even have to count pi electrons. The only time you count a pi electrons is if you have a compound that meets all 3 of these. And then you've got to decide, is it aromatic or anti-aromatic? Okay, so here we have these compounds. If we assume that these annulenes are planar, okay, so they're planar, then can you count the pi electrons? So that's 2, 4, 6, 8, 10, 11, 12, 13, 14. 14 pi electrons. So 4n plus 2, and these are just 0 numbers. So that's 2, 6, 10, 14. So 14 meets Heckel's requirement, so this is aromatic. Wow, what's this one? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, and then another 4, 8, 4, 16, 17, 18. So 18 does meet Heckel's requirement. These are both going to be aromatic. Here we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, but it's not aromatic because it's not planar. So you don't even have to worry about that. This is going to, it's not planar. So you would have to be told that. Okay, so these are polyaromatic, polycyclic aromatic hydrocarbons, and these are planar. So, and then 10 electrons, 14 electrons. So these are aromatic. And you're just showing you that they have resonance structures. Okay, now, heterocycles. When do you, so the question you need to know is when do you count the lone pair on your heteroatom as a pi electron? Because sometimes you don't count it. So here we have 1, 2, 3, 4, 5, 6. This is 6 pi electrons. We do not count it. So we do not count that pi. We do not count that one. And so what's happening is this is an sp2. This is sp2. This is sp2. And this has 1, 2, 3. That lone pair is in the sp2 hybrid orbital. So it's not participating in the pi. The pi electrons are in the unhybridized p orbitals. And so there's 6 of them. And so 6 is the 4n plus 2 Heckel's number for aromaticity. So this is aromatic. And this is actually called pyridine. And it's an aromatic. Okay, what about this one? So here we have 1, 2, 3, 4, 5, 6. This has 6 pi electrons. This time we do count the lone pair on the nitrogen. And so you can see here, this is sp2, this is sp2, sp2. You see those pi electrons are actually in the unhybridized p orbital. So that's 1, 2, 3, 4, that's 6 pi electrons, which makes Heckel's aromaticity. So when there is if once you have your heteroatom is double bonded, it has a double bonded, do not count the lone pair as pi electrons. And that's the best way I can tell you, kind of a little trick. So you see how nitrogen does not have a double bond? So this time we do count it. So you do not count if there's a double bond. Double bond, do not count. This is just showing you kind of some electron models. These are showing you biologically active heterocycles. So histamine is a biological active molecule that is this aromatic? Well, is everything sp2, sp2? They're sp2, sp2, sp2. So they're all sp2. That's fine. How many pi electrons? Well, you have these 1, 2, 3, 4, 5, 6. You see the 6 pi electrons? Notice we did not count these because the nitrogen here is double bonded. If it's double bonded, we don't count them. Okay, so 6 pi electrons, and yes, it's aromatic. And you can see that these electrons on this nitrogen reside in this sp2 orbital, but these lone pairs are going to be in the unhybridized p orbital. Okay, so sometimes we have ionic aromatic compounds or not. Ionic can be cations, which are positive charged heteroatoms, or not heteroatoms, even carbons, or anions. So they can be negative, and the negative always has a lone pair there. Okay, so, and they can be aromatic. So here we have a charge, a formal charge of -1 on the carbon. And so you're going to count 1, 2, 3, 4, 5, 6. So 6 pi electrons. Everything's sp2 hybridized carbon. So this is aromatic. And so what that means is those electrons can delocalize into that ring. And you can draw all these resonance structures. Now what about cyclopentyl diene, the cation? Well, you only have 4 pi electrons. And this carbon is a carbocation, so they're all sp2. But 4 pi electrons is anti-aromatic. Okay, so this is going to be less stable than a non-aromatic compound. And here you got the radical, and you got 5 electrons. That's going to just be not aromatic because it doesn't contain the 4 pi electrons, nor does it contain the 4 n plus 2. So this also explains why the pKa value, this is an sp3 carbon hydrogen. Do you see that? That's sp3. sp3 carbon hydrogen pKa value is 50. But this one is 15. 15 is like as acidic as the proton on water. So why is that happening? Because if you take a base and you deprotonate that, you make a cyclopentadienyl anion, and this is aromatic, and it's lower lower energy, majorly stable, and that's why it has a pKa value of 15. A tropyline cation that has 6 pi electrons, everything's fully conjugated cyclic, so that's going to be an aromatic compound. Okay, so here's the Diels-Alder reaction. What you'll want to do is you'll want to rotate, this is review. You're going to want to rotate that diene. Let's see, 1, 2, 3, 4. 1, 2, 3. And if this goes this side, this goes this side. You see how they're cis? Those are cis. Okay, so here is 1, 2, 3, 4. This is your diene. And then you have the, this should be a linear, because of sp carbon. Okay, so this is your dienophile. There's 5 and 6. And then you can draw your curved arrows. And then your product is going to be a 6-membered ring. 1, 2, 3, 4, 5, 6. You still have another double bond there, CN, and then on carbon number 4, you have a methyl group, and then this bond here would be a double bond there. Now you see that the substituents are 1, 3 to get each other, so that's meta. Remember, you only want ortho at para. So what we're going to have to do now is we're going to take this dienophile and we're going to turn it upside down. And so you can see that this is now 5 and 6. And so this is going to react this way. And then what we will get one, 2, 3, 4, 5, 6. There's our double bond. There's our nitrile. and then we have our double bond between the 2 and the 3, and then we have the 4, and you see that's 1, 2 substituted, so that's going to be ortho. So this is the correct answer, and then it's a matter of finding. This is 1, 1, 3, this is 1, 2. So C is your answer. More Diels-Alder, so retrosynthesis, we got to think back of the starting material, so the best thing to do is number those and then put your x's between 1 and 6 and 4 and 5, and then you see that this is your dienophile here. One, two, three, four, and then between 5 and 6, CO2H. And so C is one of them. And I don't see the other one, so that's your diene. Okay, this is a fill in the chart for aromaticity and classifications. You have this in your POGL. So what does that look like? This, you see this is an sp3 carbon. So even though it has 4 pi electrons, it's going to be not aromatic. The reason is it's not fully conjugated. So this is what you need to be able to do here. We're going to count these electrons. That's going to be 6 pi, and it's going to be aromatic because the reason, one, it's cyclic, it's planar, it's fully conjugated, and it has 4n plus 2 pi electrons, which are 6. This one, we have 4 pi electrons. It is going to be anti-aromatic, and it has criteria 1 through 3 above, but it has 4n pi electrons. This one we have 6 pi electrons. It's going to be aromatic, and it has criteria 1 through 3, and it has 4n plus 2 pi electrons. This one right here, we have 8 pi electrons. It's going to be anti-aromatic, and it has criteria 1 through 3, but it has 4n pi electrons. So when n is 2, that is 8. Which of the following molecules is aromatic? This one, you find that it's not planar because it's the 8-membered ring. It's talked about in your textbook, or the tub, so that's not planar. This one has 6 pi electrons, so that one's going to be fine and it's fully conjugated. This one has 8 pi electrons. This is going to be anti. And then this one, do we count those pi electrons? Yes, we do, because the nitrogen does not have a double bond. So A and D are aromatic. Okay, so this is just the basis for the Huckel's rule. These are the 3 criteria that determine whether a compound is going to be aromatic or anti-aromatic here. This is molecular orbital theory. I am not going to teach this. It's important, but I'm not going to exam over it, so you can read it on your own. And you can look through these slides if you need to, but it explains why you get extra stability for a aromatic. It also explains why anti-bonding and anti-aromatic orbitals are destructive and less stable than not aromatic. And so, yeah, I'm going to bypass this. So, but you can study this if this is something you need. And I will leave the slide here. All right, and that pretty much concludes our discussion.